Today we're talking about adding up the terms from a geometric sequence, and that's called a geometric series. I just wanted to do a quick review of what arithmetic series looked like. Remember when we had a formula that was sort of in an mx plus b kind of form? That's a good giveaway that you have an arithmetic sequence. And there's kind of a couple ways we could do that. We could add the first through the third term by actually finding the first term, plugging in a 1 for I. The second term by plugging in a 2 for I. And the third term by plugging in a 3 for I. And then we could say that the sum of all of those is equal to -3 plus 1 plus 5. That's 3, right? Beautiful. Now there was also that shortcut for finding the sum of the first 3 terms. That's where we took the number of terms divided by 2 times the very first term plus the last term, which would be the third term in this case. And 1.5 times 2 is 3. So 2 different ways to get the same answer. Sometimes this is considered a shortcut because if we were adding up the first 100 terms, that would definitely be a shortcut. Let's talk geometric. So geometric, same idea. We're adding up, in this case, the first through the third terms of this sequence. And we could just find them one after another, right? A1, A2, A3 by plugging that into our calculator. So 8 times 0.75 to the 1 is 6. And 8 times 0.75 to the 2, 4.5. The third term, 8 times 0.75 to the third, 3.375. And so the sum of the first 3 terms would then be, oh gosh, what is that? 13.875. Now that wasn't a shortcut, right? If this had been the first 100 terms, we can't use the formula back here because that formula was only good for arithmetic sequences. So, oh goodness, I hope there's a shortcut. I hope there's a formula for adding up a bunch of terms in a geometric sequence, don't you? Yes, it's a formula. So anytime I see a geometric sequence being added up, and you can tell it's geometric because it's going to look sort of exponential rather than linear, right? Do you see how all of those have exponentials in them? That's your giveaway that it's a geometric sequence. And here we notice that we just need the first term, r, that common ratio or the multiplier, and then the number of terms that we're trying to add up. And that's our formula. Let's try one of those out. So here I'm adding up the first 20 terms of the sequence defined by this. I'm going to need to know A1, the first term, when I plug in a 1 for I. 1 minus 1 is 0. 1/2 to the 0 is 1. So the first term is 600. Then I'm going to do 1 minus the multiplier. The common ratio is that 1/2, the thing that's being taken to the power. And to the n, we're trying to add up the first 20 terms. So we're going to type in 20. On the bottom, 1 minus the common ratio again. One thing you want to be careful of is when you type this in, you have to be careful. Personally, I'm going to type in that 1/2 as 0.5 because I think that's easier. But what you're going to want to do is make sure you have parentheses around the top and the bottom of this so that it knows that those two are grouped together. I think you should probably give that a shot and see if you get the same answer as me. I am getting 1,199.99 rounds to 9. I think that's approximate because as you do this 20 times, your final terms there are going to be so small. And this next one, working just very much the same way. I can tell it's a geometric sequence because it's an exponential formula. And I'm adding the first through the 100th terms. That's a lot of terms. So I'm glad we have a shortcut. The very first term is where we would plug in a 1 for the I. 12 times 1.4 to the 1 is 16.8. And then I'm going to take the 1 minus my common ratio this time to the 100 for the first 100 terms to be added up. And 1 minus 1 minus 1.4. And where are you going to put the parentheses when you type that in? Right here. I thought it might be good to actually show you what the calculator looks like when I have that typed in. So you don't need tons of parentheses. As long as you group that top and that bottom part together, you should be good. You'll notice this one comes out in scientific notation. And the reason for that is this was an exponential growth. That 1.4 is going to make those terms higher, and they're going to grow exponentially. So those numbers are going to get super big pretty fast, and we're adding up the first 100 of them. So that's actually our answer. It's just a humongo answer. And so we are just going to write that in scientific notation. We'll go 722 times 10 to the 16th power. That was a big old number because we added up the first 100 terms of this sequence. The first term is only 16, but as they keep growing, they accumulate pretty fast. So that sum formula is not bad to use as long as you know the first term. And in this example, I do know the first term. It is 24. I'd also have to know that it's a geometric sequence. I'd have to be able to figure out a common ratio, and I have to know how many terms I'm adding up. That's the numbers required in the formula. Is this a geometric sequence? Remember, the good way to check is if we take 96 and divide by 24, we get 4. What happens if we take 384 divided by the one that came right before it? We get 4, which is a good sign that this is a times 4 sequence. That makes it geometric. So we're in good position there. We have a common ratio of multiplying by 4 each time. The one thing that we don't really know, I guess we could go crazy with our calculators, we don't know how many terms we're adding up. There's ... who knows? Is that the 5th term, the 9th term? We can't tell right now. So we're going to start setting up. It asked me to use sigma notation because I'm adding up, and I'm going to start with that first term. And this top number is to be announced because, again, I'm not sure how many we're adding up, but we could easily make a formula for this geometric sequence, just like we learned how to last time. The first term times the common ratio, and we usually write to the n minus 1, but this one's I minus 1 since we used I as the index. Are you ready to figure out how many terms we're adding together? So here's a nice way to do this. This is really lovely. You know how our formula goes an equals 24 times 4 to the n minus 1. So I just need to figure out, is this a12, a13? So I'm just going to plug that in. I know that that's some certain term. And I'm just going to use my algebra and solve that equation. How do we solve an equation like that? Well, we can't combine the 24 times 4 or anything. So we'll have to start by dividing both sides by 24. And that comes out to 262,144 equals 4 to the something. And I'd really like to get that n by itself, but how do we get that n by itself when it's up high like that? How do we cancel it out to get an exponential solved? Well, the inverse operation on an exponential is a logarithm. So we're going to do log base 4 of both sides. Remember, log base 4 and 4 to an exponent are inverses, so that's the inverse operation that cancels out. You just type in log base 4 of 262,144, and it turns out that's 9. 4 to the 9th equals that number. One more step, add a 1 to both sides, and what did we just find out? We found out that this number right here is A10. That is the 10th term in this sequence. We can finish our sigma notation, then we are adding the first term through the 10th term. So there's part of our answer. We're supposed to write that series in sigma notation. And now let's find out what the answer is. The sum of the first 10 terms would be that first term times 1 minus the common ratio to the 10 over 1 minus 4. Remembering your parentheses, grouping the top and the bottom. Should be able to get that typed in. What does that come out to? Over 8 million. Fantastic, just for the first 10 terms. So that's a little lesson on how to do geometric series with our little shortcut formula.